Ladies and gentlemen, esteemed colleagues and students, and especially Professor Clark's family and friends, very welcome. Welcome to the inaugural lecture by Professor Amy Clark, Professor in the Department of Chemistry. My name is Professor Gwen van der Velden. I'm the Director of the Warwick International Higher Education Academy, and I have the great honour to open this inaugural lecture, which has been organised jointly by the Department of Chemistry and the Academy of Educators I'm responsible for. A specific welcome to the fellows who are here. We're here today to celebrate and inaugurate one of our esteemed fellows of our academic community who's excelled in learning and teaching leadership at the University of Warwick, nationally and internationally. Recognition of academic distinction at any level is a means of stating our values as an academic community and as part of the national and international community of scholars. Professorial recognition is a statement about the exceptionally high regard we have for a specific colleague, the quality of their achievements until the point of recognition, and also the expectations we have on them for the future. By accepting the role of professor, we're also understood to accept and defend the academic principles of collegiality, academic freedom in research and teaching, and in our interest in the furthering of the academic body of knowledge and the societies we live in. Professorial recognition is therefore not awarded lightly and deserves celebration, for example through an inaugural lecture such as this. Of course, specifically when professorial recognition is awarded for teaching leadership, as is the case for Andy, the lecture is perhaps an even more appropriate means to make a public statement. For those of us perhaps less acquainted with an event such as this, it may be useful if I set out the order of the event. During an inaugural lecture, the newly recognized professor has an opportunity to speak about any theme or topic of their academic interest. The lecture will always be given with the audience in mind, which is generally made up of interested colleagues and students, supportive family and friends, and interested members of the wider public. Before the inaugural professor starts their lecture, he will be introduced by a member of the senior management team of the University of Warwick, and in this case, that's the Deputy Pro-Vice Chancellor of Education, Professor David Glenburn. Thank you, David. The inaugural professor will then speak on their chosen topic for around 40 minutes. And you are invited to ask any questions you may have. Questions for clarification are most welcome, as are invitations to debate or discuss. The question session will be chaired by Professor Mike Ward, Head of Chemistry. There we are. Thank you. And Professor Ward may also wish to give a short closing address. This, of course, is a bit that Andy will be terrified. After these formal parts of the inaugural ceremony, you are invited to congratulate Professor Amy Clark on the drinks, which will be available outside the lecture theatre. Go out that door and return left. I hope you will enjoy the lecture, and I would like to thank you in advance for your interest. I'm very pleased to now hand over to Professor David Glenburn.
Ladies and gentlemen, students, colleagues, it's a great pleasure for me on behalf of the University to welcome you to Andy Clark's inaugural lecture. Andy was brought up in Surbiton. He was an only child, and then, as now, he was quiet, shy, unassuming. He loved reading books. He was always interested in science and space. He developed an early interest in chemistry. His parents and his father's here today brought him a chemistry set which Andy enjoyed. Fortunately, Andy at that time didn't have an interest in explosive devices. That was to come later. He was a bright child. He was able to skip a year at junior school, a feat he repeated at the grammar school. And there his chemistry teacher had a profound effect on Andy, apart from cultivating an interest in explosive devices. And he remarks that his teacher made him focus, and he's remained focused ever since. His twin academic interests at school were physics and chemistry. He would be the first in his family to go to university. Chemistry was the obvious choice for him, and so for that matter was King's College, London, where he did spectacularly well. He graduated at the age of 19 with a first-class degree. He carried on at King's. He gained his doctorate at the age of 23. From there he went to Columbia University in New York as a postdoc research assistant, which is where he was, he recalls, when the first Gulf War started. His experience at Columbia was among the most formative of his career. There he worked with Professor Gilbert Stork, about whom I know Andy will say more later. Stork was 70 when Andy actually arrived to work with him, and Andy undertook research and supervision in the area of total synthesis. In the opinion of many, Gilbert Stork was one of the top 5 organic chemists of the 20th century. He was an exceptional man. And Andy says that one of the things he learned whilst working with him was that he allowed you to fail. Failure was not a waste, because you learn from it. And that's a lesson Andy has applied in his own approach to educating students. There are a legion of stories about Stork. It is said that when driving and talking to his passenger in what came to be known as the death seat, he would talk to him, he would look at the passenger rather than at the road ahead. Andy says Stork exercised considerable influence over him. I hope it didn't extend right now. But one of Andy's recent publications, which came out last year, was co-authored with Stork and published shortly before Stork's death. From Columbia, Andy returned to England as a postdoc at Nottingham, and then the following year he secured his post as a lecturer in synthetic chemistry at Warwick. And since coming to Warwick, he's published extensively in leading journals. He was awarded the SCI Prize for Promising Researcher under the age of 30, which was presented to him at the House of Commons. He's published an A-level textbook. He's been commissioned to write 2 undergraduate textbooks. He's secured major research grants and contracts, developed patents, been involved in spin-off companies. But it was teaching which really engaged him. He enjoyed it, and that's the first requirement of any successful university lecturer. He has won the McCanley Prize for teaching on 3 occasions. He's taught extensively at all levels, been director of graduate and undergraduate studies. He's developed and introduced new courses, led curriculum development in the department. He's designed new and existing courses with external experts. He's managed the department's teaching strategy, dealt with RSC accreditations, and inevitably has found himself drawn into academic governance structures. He's, of course, now the university's academic director for undergraduate studies, with responsibilities across the institution. And of course, it's not just Warwick that's noticed Andy's all-round excellence. His work's been disseminated at world shows, public educational displays at the Eden Project. He's collaborated on the Eco-1 racing car, which has appeared on Top Gear, and I'm also told on the Richard and Judy show. He's been involved in developing a sustainable Formula 3 car. He's also delivered invited lectures in a tour in New Zealand. And Andy embraces the responsibility which comes with teaching. The impact of an educator is to inspire, to engage, to inform, to build independence in students, disciplinary expertise, strong scholarship, a genuine interest in students, an exceptional passion for teaching. These are characteristics that we at Warwick value in our educators. We take considerable pride in the impacts teaching can have on our students. Our students are critical, they're independent thinkers, they're well versed in their disciplines, but they also look outwards, beyond the boundaries of those disciplines. They're constantly challenged to take on new experiences and to drive themselves forward intellectually. Warwick would not be able to engage learners in this way if it wasn't for educational leaders in each of the disciplines who enhance the curriculum, improve teaching, introduce new assessment methods, find the smartest minds to study at Warwick. Those who achieve on all those fronts are genuinely in the right position to profess. Ladies and gentlemen, students, colleagues, Professor Andrew Clark.
David. I'm not really sure I can follow that, but I suppose the best hat. I'm going to take this hat off because it makes me look absolutely ridiculous. So that's the first thing we will do. This is just a placement slide, you probably worked out it's me. This is the title of my talk, The Life and Times of a Radical Chemist. Now, those chemists in the audience will of course know what that probably means. The non-chemists in the audience have probably got an idea which will turn out to be wrong. In any case, I should educate you as we go along. So we're going to start off talking a little bit about my life, what inspired me. We'll talk about some of the chemistry that I've done in a way that hopefully we can all understand. Then we'll talk a little about some teaching, and we'll come back to some more chemistry and some more teaching and so on. So we'll start at the beginning. This is me as a little baby with my mother and father. I've still got this penguin in my bedroom. I don't think I should really admit to that. But, there we have it. Okay, so David has already sort of mentioned that when I was a child, I was actually interested in astronomy more than chemistry. And these are some of the pictures I've taken with my telescope because I'm interested in astrophotography. And so what I've done is I started with a quote from somebody who was a hero of mine, from Carl Sagan in 1996, and I think it's more apt today than it was back then. And it's, "We've arranged a global civilization in which most crucial elements profoundly depend on science and technology. We have also arranged things so that almost no one understands science and technology. This is a prescription for disaster." And of course it is. Okay. Now, if that wasn't depressing enough, in 2014, the government commissioned a survey on public attitudes of science. And out of the ordinary questions that were asked, this is one of them with the percentages. So, scientists adjust their findings to get the answers they want. 35% agree, 34% disagree, and perhaps more worrying, a third don't know. Okay? Now to me that's quite frightening. We have to think about why that might be. Now, I can see somebody in the audience who I'm going to plagiarise. And it's Professor Kevin Moffat sitting in the middle. So one of the reasons why perhaps the general public feel like this is because the people that govern us, our politicians, and the people that run our media tend not to have a scientific background. I mean, if you look from the last election at MPs and what degrees they did. Now, first of all, not all MPs have a degree. That's a good thing. We want a representative democracy which represents all of the population. But you can see that the majority do social studies, law, sorry David, I know you're a historian, history and languages. And that's perhaps not surprising because people go into politics because they want to perhaps change the social order. But there aren't very many people that know about science. In 2017 there were 2 MPs that had a chemistry degree. One from the Conservative Party who has a PhD from UCL and one from the Labour Party who has a BSc from Sheffield. Now, when they were in power and were given a job, what did they get given? Well, the Conservative with a PhD in chemistry was given a job in the Culture, Media and Sport Ministry. So we have very few people with a scientific background, but those that we do, we don't even get in the right jobs. If you think about who is in charge of universities and science funding, it used to be Joe Johnson, the brother of buffoon Boris. Now we have Sam Diana. I can't pronounce his surname. Well, what did they do? They're in charge of science funding. They both went to Oxford. One did PPE and one did, sorry David, history. So one of the things that I'm quite passionate about, actually, and I don't think we do this very well in this university, is make sure that our scientists also know something about politics, also know something about communicating science to the general population. The university, and through people like Kevin, do this very well, are very good at outreach. But I think we spend a lot of time with outreach with children in schools, and perhaps not enough time with thinking about how we deal with the general population outside of school children. Okay, let's have a quick potted history of my life. I've already heard from David that I went to a grammar school. I passed 11 plus when I was 10. I thought I was really clever, and I was really confident. And then I went to secondary school, and I found that I was near the bottom of my class, actually, and I lost all my confidence. And that really stayed with me for a very long period of time. Primarily because of the blazers we were forced to wear. Here we look like a bit of a bizarre, demonic barbershop septet. This is our first day at school, and the one thing that this blazer did teach me was how to survive being bullied, because we had to go on a 3-mile journey every day past the local comprehensive, which had an ordinary blazer that was just a nice black one. And because, I'm sorry David, I keep on doing this, but because David has introduced me and is a historian, I thought I would share with you some of my old school reports. Those that went to my wedding may have seen this already. So this is a school report from history in my O-level year. 48%, 17th equal in a class of 20. Andrew is keeping his head above water, but not swimming strongly. I reckon if we could give feedback to students like that today, everyone would get their feedback within 20 working days. I'm glad that we can't do things like this these days, because again, when you see something like that, it starts to eat a little bit into your confidence. So let's go to my A-level year, Mox. He has worked consistently throughout the year, but never featured prominently in class discussions. Of course, you know where that's going. That's chemistry. So perhaps I shouldn't really be standing in front of you. I feel a little bit of a fraud. But what this tells you is I was quite a late developer when it came to education. And it reminds me that we all come to education in a slightly different way. We've all got different routes, we've all got different backgrounds. And academics tend to have been moderately successful when they come through the school system. And they think that the best way of teaching is perhaps how they were taught. And they don't necessarily realise there's a whole range of people that have got different experiences, learn in different ways. And we need to always consider that when we're designing teaching and courses. Okay, perhaps one of the reasons why I wasn't very good at school, and again I keep on coming back to Kevin, I'm sorry, he's right in the middle, so my eyes are drawn to him, was that I was interested in music.
Yes.
So when I was 14, I was in a band. We looked pretty cool, don't we? When I was 15, I was going through my Rick Wakeman period. I'd obviously thought about an academic career because I'm wearing academic dress already. By the time I was 16, I'd moved on to the sort of dark part of my personality as a zombie. Yes, that really is me. Okay. So, I went to go and do a chemistry degree. So for the people who don't know any chemistry in the audience, we can think of chemistry as effectively being 3 subdisciplines. There is organic chemistry, which is the chemistry of the element carbon, and most of the applications tend to be in medicine and biology. Inorganic chemistry is the chemistry of every other single element in the periodic table other than carbon. And physical chemistry is the chemistry of measurement, analysis, things called spectroscopy and theory. Now, when I was at university, it was in the 1980s, and in the final year I wanted to do a research project, and I was wanting to do an interdisciplinary project. And I wanted to be right there in this Venn diagram, because these things often overlap. So, for example, you can have molecules which have, say, metals bonded to carbon in this area. That's organometallic chemistry. What I wanted to do was a final year project in organometallic reaction mechanisms. Something in those days wasn't a big area. But I'm very unlucky in my life, generally. Things don't always work out. But that's not true. Sorry for this. I didn't get the project, I got the wife I wanted, but I didn't get the project. Instead, I got a project sort of in between organic chemistry and physical chemistry. I was looking at kinetics of organic reactions. Effectively, what that means is the rates of organic reactions. And actually, it profoundly changed my life, because I'm, in fact, an organic chemist. And it reminds me, I didn't want to do that. I was horrified. I wanted to complain that I was given that project. And it reminds me that sometimes we actually need to make students do things that they don't want to do. Because often it's very easy and comfy to stick in the cosy options of things you want to do. But sometimes you need to be forced outside your comfort zone, because it can actually lead you somewhere completely different in your life. Anyway, I decided to do a PhD in organic chemistry with the title Nitrogen Heterocycles via Radical Cyclization. The non-chemists in the audience are getting a bit worried now. I'm going to explain what that means, hopefully in ways that you'll understand. As long as you know what a square is and a pentagon, you should be okay. Okay, first of all, let's look at the word radical, because that's in the title. And if you look at the Oxford English Dictionary and you look at the definition, there's an adjective definition and there's a noun definition. I won't go through these, you can start reading them. But, you know, characterised by departure from tradition, innovative or progressive, very good and author-driven. I quite like to be associated with those sorts of phrases. We perhaps consider the noun as normal, you know, a person who advocates thorough or complete reform. But in chemistry it means something different. You know, the non-chemists probably know that chemical structures are made of atoms, those atoms have electrons in them, and effectively radicals are atoms or molecules where an atom has an odd number of electrons. Okay? Now what's interesting about radicals is that normally makes them excessively reactive, so reactive that we perhaps can't control them. And I was fascinated about whether we could use these almost uncontrollable intermediates to make things of importance. We represent a radical by a dot next to an atom, so this is a carbon atom, so that's a carbon radical. You may have heard of radicals in terms of ageing or in cancer, for example, as well. So this is a slide which will be a sharp intake of breath for the non-chemists. But as I said, all you need to do is be able to understand shapes. What we've got here is bonds, so a line represents a bond between two atoms. Now, nitrogen heterocycles are effectively rings of atoms where there's a nitrogen atom. And why I was interested in these is, here's some figures from 2014, 59% of all small molecule drugs contain a nitrogen heterocycle. So if we can find ways to make nitrogen heterocycles, we're going to get a way into a whole variety of interesting molecules. So a heterocycle with nitrogen in can be seen here in blue. So here we've got a square, a four-membered ring with a nitrogen atom. Okay? This is an amoxicillin, an antibiotic which most of us might have had unless we're allergic to penicillin antibiotics for something like a lung infection. We can have a five-membered ring with nitrogen, or a six-membered ring with nitrogen. This is a bit difficult to see, but there's 1, 2, 3, 4, 5, 6. We can have a seven-membered ring with nitrogen. We can have various ring sizes. Now these are all relevant to my family, I think. So, I mean, I take this because I have high cholesterol. My brother-in-law has epilepsy. My father-in-law has GERD, and so we have this reaction where we've got two nitrogens in a five-membered ring. Unfortunately, my mother can't be with us because she died some while ago of motor neurone disease. I'm sure she'll be very proud of me standing here. But this is the drug for treatment of motor neurone disease. It's a nitrogen heterocycle five-membered ring. And my dad has ocular hypertension, so I put this one in. Again, now we've got a five-membered ring and a six-membered ring with nitrogen. So the ability to make nitrogen heterocycles is quite important. And that's really what I've spent about 15 years of my life doing. How do you do this? Well, what you do, the idea is you take effectively a linear set of atoms like this. Don't worry about the bromine, and don't worry about this at the end. What we're going to do is we're going to make one of these very reactive radicals. They're so reactive, they're then going to bite back and we're going to form a ring. That's the idea of the chemistry that we're going to do. So we come up with some chemical reagent, we make the radical, it's so reactive, it bites back in some way, and we effectively get a ring, and then we have another chemical reagent which turns that radical back into an ordinary molecule. To make a nitrogen heterocycle, all we've got to do is put a nitrogen atom somewhere in this chain of atoms. So we're going to look at something like that. Now the state of the art when we started looking at this, the chemical reagent that you needed to use was one based upon tin. This is it. And the problem with this, it's very toxic. It's toxic down to parts per billion level. It's a neurotoxin. So you have to make sure you've got rid of all of it if you're going to make a drug using this approach. And it's very difficult to get things that pure. It's very, very expensive. And not only that, the reagent itself is quite expensive. You know, 10 grams, 30 pounds. If you want to make 10 tons of a drug, that's a hideous expense. So it comes as no surprise that no pharmaceutical companies, despite the fact that nitrogen heterocycles are everywhere in drugs, have used this approach. And that's one thing I wanted to try and change. So, can we develop cheap, non-toxic reagents to make these nitrogen heterocycles? Can we make all of those ring sizes that you saw? And what we did was, we took a trick from nature. So this is vitamin B12, something that we've all heard of. Perhaps we've not all seen what the structure is, that's not important. But vitamin B12, what it does in the body is it mediates these radical reactions. So can we use it to effectively do these transformations? And the answer is yes, we can. We particularly made this nitrogen heterocycle. It's got 2 of these heterocycle units appended to each other. And I chose this one because, again, because of my dad, it's used in glaucoma treatment. It's found to be a neurotransmitter inhibitor. It also was, in the last 15 years or so, found to improve long-term memory. So there was a big, big push to see whether this could be used in clinical trials for Alzheimer's. Unfortunately, it failed. So it isn't a particularly useful drug in that regard. And then, one of the very first grants I had, postdoctoral grants, was with Dave Hamilton, who I can see sitting right at the back there, where he was looking at trying to capture radicals to make materials, and I'm trying to look at ways of capturing radicals to make these drug-type molecules. And we looked at a whole range of other types of catalysts, not ones based upon vitamin B12, but ones based upon iron and copper. And effectively, we can use very little amounts, 0.1% by weight, of copper bromide or copper sulfate, which is very, very cheap. And we can use things like vitamin C, which will actually do the reduction that we need in this particular reaction. So, we've made a whole range of molecules, 4 membered rings, 5, 6, and molecules with a whole variety of functionality. What was interesting in this is that between 1974 and 1993, there's 22 papers in this area. But from 1993 onwards, there's 568. There's 200 in the last 2 years. This might not be the time when I've decided to give up this area of research. But I have been one of the pioneers in this sort of chemistry. Okay, so David has already told us about one of the guys that I collaborated with in my postdoc work, Gilbert Stork. He was a fantastic man. As he said, he allowed me to fail, and that's one of the things that I think is very important. Students need to be given the space to fail without feeling as though they're going to be criticised. Some of the problems that we've got at the moment, of course, is that students come, they're paying £9,250 per annum, they feel as though they've got to get a first, otherwise it's a failure. They haven't got an opportunity to fail. They think that everything that they're going to do is going to be assessed. And that is something which allows you to learn profoundly if you fail, if you think of experiments and they don't work. Gilbert Stork was the sort of guy that would be quite happy with the fact you'd wasted £10,000 of his research budget because you'd gone off in the wrong direction, because you'd actually learned something important. It might have been negative, but actually the way that you've learnt about chemistry had been influenced in that direction. I think one of the things that we can do about Gilbert is look at his obituary, which was from the editor of the Journal of the American Chemical Society. He says, "Few people in the field of organic chemistry command such deep and unanimous reverence as Gilbert Stork. His impact on the field of synthesis is hard to overstate. His research spanning an incredible 8 decades. Just think about that. He was in the lab for 8 decades. He was in the lab 1 month before he died at age 95. And that's fantastic. I won't read all of this. I'll just highlight for the chemist in the audience, some of the things that he's been responsible for include radical cascade reactions, the word radical, but that's why I was interested in working with him. Annulations and enolate chemistry, to the very act of stereospecific synthesis. So the chemists in the audience might not have realised that the very first person to make an organic molecule stereospecifically with control of stereochemistry on purpose was Gilbert Stork. And now that's something we expect our first year chemists to be able to do just as a matter of fact. So that really was a revolutionary thing that he did. So this is the last paper he published, and there's my name. And you might not be able to see, but there is a 6-membered ring with nitrogen. It's a nitrogen heterocycle. So you can see why I was interested in working with him. Okay, so the students are either lucky or unlucky depending on your point of view, because apart from their introductory lecture, which they will have from Claudia, I'm not quite sure where she's gone, but there she is, as the new Director of Undergraduate Studies, the first actual teaching they get is from me. One of the things I like to try and get students to do is to think about things, as I've said, without feeling that if they've got something wrong, we're judging them. I want them to try and work out outcomes from information which isn't complete. That's one thing that students find difficult. And this is my first slide. It says, the only reason people do not know much is because they do not care to know. They are incurious. Incuriosity is the oddest and most foolish failing there is. So because I'm an organic chemist and I'm interested in medicine, what we do is we look at the oldest medical treatise that there is. That is the Ebers Papyrus, which is an ancient Egyptian book where they read that they've written down all of the ways that they used to treat various ailments. And we look at how they used to treat bite-toothed crocodile. It's a bit of a sensationalistic thing in that. Not something that happens in downtown Coventry, I imagine, but perhaps did on the banks of the Nile. Now, this isn't really about how the ancient Egyptians treated bite-toothed crocodile. It's more about how they treated terrible wounds. Sharp intake of breath there. Yes, of course, this is me. I'm pretty accident prone. That's when I cut my thumb off about 6 or 7 years ago. So, how did the ancient Egyptians treat quite bad wounds? Because, of course, what can happen is they can get infected. They could go gangrenous, and you could die of septicemia. What they did was, they got raw meat, and they rubbed it into the wound, and then they put a bandage on it. And then I tell the students in groups to work out, is there any scientific basis in that? Can they think of any way that there may be a scientific basis in that? Can they think of any experiments to try and sort that out? And basically, they can talk in groups, come up with weird ideas, and not feel as though they're being judged. Most of them think it's a load of bollocks. If you think about it, ancient Egypt, pretty hot, no refrigerators, flies landing on the meat, flies laying eggs, eggs hatching out into maggots. What we know about maggots is that they eat necrotic and gangrenous flesh, and they do not eat flesh which is alive. It's a way of actually tidying up wounds, so much so that in 2004 you can get maggot therapy on the NHS. The FDA in America use it for debriding non-healing necrotic skin and soft tissue wounds. So, looking at something which is ridiculous, I try and teach the students never ever throw something away because it looks ridiculous. Always think about it. Always research something no matter how silly it seems, because there may be something which will lead to something that's beneficial. And more recently, studies have shown that maggots destroy a whole range of bacteria, including methicillin-resistant Staphylococcus aureus. That's the MRSA superbug that we hear about, that we often find in hospitals. Okay, every 10 years I get bored and I have to reinvent myself. Okay? So I had a year sabbatical with Greg Chalice, learning about molecular biology, learning how I could knock out genes and do stuff like that. And we became interested with a range of people, whose names are up here, on something called drug reprofiling. Now, the average time to get a drug from discovery to market, difficult, but it's about 12 years. And the problem there is the patent lifetime is only 20 years, so 12 years is gone. You've only got 8 years to get the money, if you're a pharmaceutical company, back that you've spent on developing that drug. And what's more, the average cost of drug development is normally in the billions of dollars. So that's why drugs are so expensive. Now, drug reprofiling is the use of known drugs to treat different diseases. If you think a drug might have a side effect, normally that side effect is not something you want to encourage. But actually, if you can see why it has that side effect, you might be able to reprofile the drug for another disease state. And the reason why that's interesting is because we don't have to go through the costly toxicology studies, because they've already been undertaken. If it's a new treatment, we can repatent and get another 20 years of life. So that's pretty good business profile. We started up a spin-out company to try and exploit this. Examples of this, of course, are Viagra, which was developed initially as a for heart disease and was found to be beneficial in erectile dysfunction. And thalidomide, of course, which was originally in the 60s an analgesic, has now been reprofiled to be used in the treatment of leprosy. Now, I go into the chemistry and the biology that we developed to do all of this, because we don't have time. But just to say, the thing I'm most proud of is this. Risperdal is an antipsychotic drug, and it's been known for a while in the literature that people who are psychotic tend to have lower incidences of small cell lung cancer, statistically. And so it might be tempting to say that perhaps this drug is hitting receptors that we don't know about in the body, which might have something to do with lung cancer. And it turns out that they do. So we can apply the chemistry, which I haven't told you about. And this has recently passed phase 2 clinical trials with an average increase in life expectancy of 1 year for people with non-small cell lung cancer, which is the majority of lung cancers that there are. Okay, let's go back to teaching again for a bit. No, actually we're not. This is just one other thing from that 2014 Public Understanding of Science Commissioned report. The benefits of science are greater than any harmful effects. 55% agree. At least it's the majority this time, and it's up 10% from a long period ago. If you think about it, the general population, because of the media, they see things where science is causing pollution, we're using plastics which are polluting the seas that aren't biodegradable, and things like that. And so, again, I decided to reinvent myself after doing some biological chemistry and turn myself to look at materials. And I'm very wary because we've got Dave Paddleton at the back who knows so much more about materials than me. So consequently, I haven't put much chemistry on here for him to criticise, but I'm sure he can if he wants. Okay, so here's some facts about plastics. In 2013, 300 million tonnes were produced annually. That's 8% of global petroleum is used to make those plastics. Now, of course, global petroleum is non-renewable. It's something which will eventually run out. I'm not going to sort of predict when that will be because no one's successfully been able to do that ever. But in Western Europe, we effectively make 100 kilograms of plastic per person per annum. Now, in Asia, it's much lower than that, but that's increasing as they become a more consumer-driven society. A lot of this still ends up going into landfill, and that is recycled seems stupidly to be put into a tanker and shipped off to China by using a huge amount of diesel to be recycled. And I'm sure we've seen with the David Attenborough programmes, that 10 to 20 million tonnes per annum ends up in oceans. There really is a big, big problem there. And I wanted to sort of try a little bit to address this if I could. So we looked at one range of plastic called the polyurethane. Polyurethanes are around in a number of applications. It can be used in adhesives, it can be used as coatings. You're probably sitting on a flexible foam, which is a polyurethane foam. The foam can be rigid, which could be used perhaps in insulation and in packaging. Now, the market for polyurethanes is only about 18 million tonnes per year and only $54 billion estimated, but it's quite a large market. Now, the chemistry involved in making a polyurethane, you need to take two components and mix the two together. What you do is you take something called a polyol, where you've got at least two alcohol groups, that's the groups you find in ethanol, and you react it with a diisocyanate and mix the two together in an appropriate proportion, you get a polyurethane. And depending upon the rest of the chemical entity between these hydroxy groups, or the number of hydroxy groups, you get all of these different properties. Now, one of the key polyols used to make polyurethanes is this, where we've got three alcohol groups. To me, naively, this looks like three things attached at one end. Now, if you know anything about biology, you might recognise three things attached at one end to things called triglycerides. So, cooking oil, rapeseed oil, vegetable oil, that sort of stuff, has three little groups attached at one end. And we wanted to see if we could prepare plastics, polyols, from renewable resources such as this. And we discovered that we could do some green chemistry to do that. So you can see there's no OH groups on here, we somehow need to add some using some chemistry. And lots of people say they do green chemistry. Actually, most of them don't. I think green chemistry means that every reagent in your reaction has to be renewable or sustainable, and any byproducts you get have to be water. Okay? That's my take on green chemistry. Just tweaking a little bit of a catalyst. No, that's not for me. So what we did was we can take vegetable oil, we can take acetic acid, which you can get, which is vinegar, effectively, and then we can use water and a little bit of acid, phosphoric acid, to make these polyols. So in other words, you can take some vinegar, and you can take some Coca-Cola. You can do this last step in Coca-Cola, and you can make these polyols. Now the problem with using things like cooking oil is we're taking oil from the food chain. We know there's a huge number of people in the world. We don't really want to be taking away from those people food that they might want to be eating. And so we've looked with White Manufacturing Group, and I can see we've got Stuart Coles in the audience, and we did this with Kerry Curran amongst others. We've been looking at waste products. So we looked at waste cocoa butter, which is the waste product from confectionery manufacture. We've been looking at plants which might grow in the weeds of people's gardens. And we've also been looking at algae oil, which you can harvest from the sea. And you can make a whole range of different polyurethane products from that. And we can make these into little dog bones that we can put in machines, and we can look at their tensile strengths, and we can see if they're elastic or if they're brittle. And so you can get these graphs which are called stress strain graphs, and all of the different starting materials, the starting byproducts that we've used, give materials with a whole range of different products. We've already heard from David. Oh no, we haven't got there yet. This is one of the last things that we've done. We've been making some polyesters from waste grapeseed oil, which is a waste product from making wine. And I would like to be able to make a polyester bottle to put in wine made from the waste product of wine manufacture. I think that's a pretty cool idea. We haven't quite got there yet. So, as David's already said, we work with WIHEA Manufacturing Group. They did 99% of this, I should say. We just had a little bit of the plastic on the Eco 1 racing car. Again, we had a very, very little bit of plastic involved in the world's first Formula 3 racing car, again done with WIHEA Manufacturing Group. And actually now, Ford, in the Ford Mustang, their foam seating is made from soybean-derived renewable polymers. Okay, let's get into some teaching. League tables. League tables are okay if you're in the top 10. Consequently, vice-chancellors like people to be high up in league tables. League tables are there for many reasons. You have league tables of power companies, you have league tables in schools, and of course you have league tables in terms of universities. Now, league tables arise by metrics, and if the metrics that they're measuring are sensible, then that league table will just drive behaviour, and everyone changes their behaviour to try and get up that league table. If those league table metrics are not sensible to your organisation or to your company, then there's probably there's a bit of an issue about whether you chase those metrics. Now, for those that don't know, the Research Excellence Framework has been going for quite a long time. This was the last time it was done. It's coming up in a few years' time. Every Research Excellence Framework period, academics' publications get effectively looked at by a government panel and graded, as does the infrastructure where they're doing their research. And chemistry at Warwick is very good at research. You can see we're 6th equal with Warwick in Imperial and UCL, and that's a pretty good outcome out of 52 chemistry departments, to put that in perspective. About 13 years ago, the government started introducing the National Student Survey, which is something where actually at the end of the student's undergraduate degree, they answer some questions about their student experience in a range of different topics, including teaching, assessment and feedback, academic support, organisation of the course, learning resources of things like IT, library and labs, personal development and overall satisfaction score. Now, Mike Shipp was here. I wasn't expecting him to be here, but I think he was head of the department at the time when he made me director of undergraduate studies. And at the time, chemistry wasn't doing very well in the league table of National Student Survey. Frankly, we were second from the bottom. And that was a pretty difficult thing to have to deal with. So what I'm going to do is I'm going to show you how the scores changed, and then we're going to talk about how we might have done that. So these are the scores from 2011 to 2014 in the different areas. So we start pretty poorly in this dotted line, and then we don't have much of a difference 1 year later. Then things start to improve, and about 4 years later, we're doing pretty well. And if we actually look at this data in terms of not percentages, but where we are in the league tables, what you find is by 2014, we're first for 3 of those areas, we're second for 1, and we're third for another. Okay. So what on earth did we do to get there? Well, one of the things, of course, that you have to do is you have to work out what's wrong, why the students are saying what they're saying. You then have to sort of make a decision as to whether what they're saying is correct or not, and then you need to make change. Now, I'm going to introduce something which some people may have seen if they were here people, other people might not. And this is something which is quite famous. It's called Einstein's ladder of citizen participation. It's nothing to do with education per se. It's to do with how people can be engaged in terms of democracy. And so it's designed for political representation. Gwen and others have thought about looking at this in terms of student engagement. This guy, David Wilcox, has done a lot, and you can find this on this website. And certainly, the higher up you go in this ladder, the better student engagement you're getting. So let's see what some of those definitions are, and you can think about in your departments where you might be. And I'm suggesting we don't get to 7 and 8. That's not really appropriate for education. 8 is effectively where all the decisions are made by the citizens. We're not necessarily saying that's something that should happen in a university. But at the bottom, rungs 1 and 2, management decides and markets its agenda. That means you're going to do this, and we're going to try and manipulate you by marketing and advertising what we're doing so you believe it's what you want. Okay? The next run up, we're going to give you some information about 6 months beforehand that we're going to do that. Okay? A little bit more in terms of engagement, but actually not really. And then we get to 4, and I've put this in italics because I think a lot of people think this is what they might do. We have surveys, we have NSS surveys, we talk to our students, we have module reviews, we try and find out what they think is good and bad. We have meetings to assess opinion, and then we try and change things. Too often, we change things, but still don't involve them in those decision-making parts when we're changing things. And we often don't tell them what we've done. That cohort might move on to the next year, and the new year don't even understand what changes you've made. They don't see that. Now, rung 5 co-ops users onto committees. All university committees have representation from the student union. A couple of years there was a decree that department teaching and learning committees need representation from students. Now, how they engage with that will be different depending upon the students in the department. But where you can make a large amount of change is where we have rung 6. Decisions are made through negotiation. It's not just listening to what they want and then making some changes. It's making those changes with them present. And we have the Student Learning Experience and Engagement Committee, which is jointly chaired by Gwen, an academic director, and the Director of Education of the Students' Union. And one of the things that we did in chemistry very early on was to get voting systems. Some of you might know about this. You can ask a question, you can vote. People don't know what the votes come from. You can use your mobile phone to do this now. And we asked a lot of questions. But you need somebody who, at the front of the lecture theatre, can interpret what they're saying and say, yes, we acknowledge that. Let's think about how we might change that, and have the authority to know that they can go back to their department and say, we need to do this, they've suggested this, we've negotiated this, and try and get change. Now, of course, you can't do that with everything, but what you need to be able to do is have a real-world conversation, I think, and negotiation. And we did that over a period of 4 or 5 years, and we still do that, I think, when it comes to NSS time. Is that true, Claudia? Yes. And I think that was one of the main reasons that we managed to increase that student engagement and increase those surveys. Now, I know I'm running out of time. I'd like to say that I've got kids in the audience, we're writing a textbook from the Royal Society of Chemistry tutorial text. And this is heavily involved with students. So you can have student co-authors, and you can have students read the text and make comments. And what will happen here is that we will write some text. The students in the margin of the textbook will say the particular areas that they find difficult generally, the misconceptions. They will then tell us, in fact, where the writing is pretty poor and actually we could do much better. So we're setting up a partnership with students in writing textbooks now. So, you've seen we have research league tables, we have national student league tables, a range of media, and try and link these two together so that we have research and teaching together. And we have the Guardian, we have the Times, and this is the 2018 Guardian league table for universities. And while it always is in the top 10, we've moved on one. So that's pretty good. Now, a few years ago comes something new, the Teaching Excellence and Student Outcome Framework, or TEF. It is designed to be the teaching equivalent of that REF exercise you saw at the start of this little mini section. What happens is a university applies and gets assessed. It's meant to be an assessment of how good you're teaching. Lots of people have argued that the things which are used to assess that aren't really good indicators of what good teaching are. I mean, for example, the things which we look at are some of the National Student Survey outcomes. And of course, student perceptions don't necessarily equate to good teaching. That's one thing where there's a bit of an issue. We have non-continuation data. That's how many people make it past year 1. We have employability, so those number of people that actually get a job 6 months after leaving university. And out of those which actually have graduate level jobs. All of these things come in to give you an outcome which can be bronze, silver or gold. And we note that the lowest you can get is satisfactory. You can't get something that's unsatisfactory in this exercise. Now, this is the last controversial thing which I will finish on. Some people have decided to weight what they believe the outcomes of the TEF with the REF have been, to produce a league table which was published 6 weeks ago in the Times Higher Education Supplement. And this is it. And now you see, when you rank TEF and REF scores, Warwick comes to number 22. And there's something which focuses minds a lot, I think, in senior management, then is that Coventry is now above us. Okay, something which has always been below us in the league tables before, often 20 or 30 places below us. Okay. So I'm going to leave it at that, because that's something which I think people will need to digest and think about, apart from the fact that subject level TEF is current, so if you're in departments, your subjects may be getting a silver, bronze or gold, and consequently your departmental league table positions may also change, and so departments start need to think about this. So I finish with a quote from another of my heroes, Arthur C. Clarke, where a distinguished but elderly scientist, I'm 50 now so I'm elderly, states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. So all I need to do is to thank my collaborators, the postdoctoral fellows I've had, the PhD students I've had over the last 20 years, and all of the companies that have funded my research, and to thank you for coming and listening and actually staying away. Thank you.